Welcome. As the lights around you soften, allow your attention to settle on a single, comforting idea: time. Think of it as a gentle, steady river. Tonight, we will drift along that river together, learning small, restful truths about why the clock on your wall seems to move only one way. Let each sentence be a slow footstep. Let each fact be a shallow, calming ripple. Breathe in. Exhale. Feel the weight of your body sinking deeper into the chair or bed. With each breath, let curiosity and calm move together, like two soft birds gliding across the same warm wind. At the heart of the mystery lies a quiet, unassuming principle: disorder or entropy. Imagine a neat stack of paper. One careful breeze and the sheets scatter. The scattered pages are more likely than the neat pile. The universe, in its vast, patient way, prefers more probable arrangements. This preference is the subtle engine that points time forward. It does not shout, it only nudges. Over untold moments, it becomes the compass by which the world turns. Consider a drop of ink in clear water. At first, the ink is compact and dark, a small island of order. Watch as it dissolves. Slowly, the ink spreads, softening into the water until only a whisper of color remains, evenly dispersed. That spreading is entropy in motion. You have not seen the ink reassemble itself into a tight bead. The likelihood of that is unimaginably small. The drop's gentle diffusion is a quiet physical law doing its slow work, nudging every moment into the next. Yet, when we look deeper into the rules that govern particles and waves, the mathematics is elegantly indifferent. Many of physics' core equations, those that describe how particles move or how light behaves, look the same forward or backward in time. If you could film a planet orbiting a star and play that film backward, the math that predicts the orbit would still hold. The equations do not insist on a direction. This is the first small wonder. At the microscopic level, the world whispers of timeless symmetry. At the macroscopic level, we wake to a sunrise we will never unsee. So how do these two truths fit together? How does the indifferent symmetry of equations yield the lived experience of a single, onward flow? The answer lies in scale. Trillions of tiny rules accumulate into a large, decisive tendency. Think of an avalanche started by a single pebble. The pebble's choice is trivial. The avalanche that follows is not. When countless particles interact, the statistics of probability tilt toward increasing disorder. The more pieces there are, the more irreversible the outcome becomes. Now let your thoughts wander gently to everyday clocks. A clock is not simply a symbol. It is a small machine that converts stored order into motion. Wind a spring and you give it ordered energy. Over time, that order disperses, friction, heat, tiny losses, and the clock's hands move. Each tick spends a fraction of order to mark the passage. If a clock could run without cost, without loss, without tiny dissipations of energy, its ticks would have no meaning. Our practical measure of time is tied tightly to the quiet consumption of order, and each used bit leaves behind more disorder than before. Breathe in, breathe out. Notice how the calmness of this rhythm matches the steady cadence of the clock, a gentle soundtrack to our exploration. Time, viewed this way, is not some tyrant marching us toward an end. It is the subtle ledger in which the universe keeps its account: order spent, disorder accrued. The ledger is patient. It favors gentle increments and long spans. On a slightly stranger scale, gravity offers its own soft hand in shaping time's path. When dust and gas clump under gravity's pull, forming stars and planets, the local region becomes more ordered. That looks like a reversal of entropy, but the bookkeeping ends well for the universe. As matter clumps, it releases enormous amounts of energy as heat and radiation. That released energy scatters and increases entropy elsewhere far more than the local order increased. Stars are, in a way, islands of temporary order paid for by a broader increase in disorder, the cosmos paying a bill with interest. Black holes are perhaps the most poetic guardians of this one-way street. When matter slips beyond the event horizon, it disappears from the world we inhabit. The process is irreversible in practical terms. The horizon's area, a quantity that can only grow when mass falls in, is directly related to the entropy of the black hole. As black holes grow, the universe's tally of disorder increases. Even in the darkest, most mysterious corners, entropy quietly writes the final chapters, and time continues its gentle, irreversible procession. Rest your mind on the idea that memory itself is an arrow. Your memories are physical changes carved into the wiring of your brain. Each time your brain encodes a memory, molecules shift, synapses strengthen or weaken, and tiny energies get used and released. Creating a stable record of yesterday requires work, and that work increases entropy. This is why we remember the past but not the future. Memory is a thermodynamic footprint. It cannot be stamped without leaving an energy trace. In the skin of everyday life, that trace is evident. Ice melts on a warm table and does not spontaneously reform. Hot coffee cools and never becomes hot again without added energy. A child builds a sandcastle that the tide erases. The tide does not pile the sand into neat towers by itself. All these are simple, observable instances of the same cosmic habit. Things tend to move from special, ordered states into more probable, disordered ones. Now we shift to relativity, a soft expansion of our view. Einstein taught us that space and time are woven together into a single fabric called spacetime. Time is not an absolute, universal metronome. If you travel very fast, near the speed of light, your time will flow more slowly relative to someone standing still. Similarly, in a strong gravitational field, time stretches and slows. These effects are not merely theoretical. They are measured every day. Satellite systems that guide our phones and maps must account for these subtle shifts, for even tiny differences would soon create navigational drift. Imagine floating in a spacecraft that moves gently faster than everything on Earth. Your clock ticks a little more slowly. Return after only a short journey and discover that friends you left behind have aged more. It sounds like science fiction, but it's a real, measured consequence of motion and gravity. Time can be elastic, stretching and compressing, but always keeping its local forward-pointing direction. There is a delicate, fascinating fact in particle physics that whispers about a deeper asymmetry. Certain particles prefer one direction of decay over another. These tiny biases, observed in certain subatomic decays, hint at why the universe has more matter than antimatter. The imbalance is subtle, but over eons it shaped everything we are. A minuscule preference at the smallest scales can ripple into a colossal asymmetry across cosmic time, allowing stars, planets, and life to exist at all. It is as if the universe kept a faint bias, a tiny tilt that favored existence and continuity. Let your eyes close if you like. Imagine a long, dark road lit by scattered lanterns. Each lantern is a moment past. The road stretches away into the night and you walk slowly, lantern in hand. The past is the light behind you. The future is dark but vast ahead. Your steps are irreversible, and with each step your lantern warms the path behind you with small, certain glow. Everyday technologies are also woven into our sense of time. The telegraph once carried news across continents in pulses of code. The steam train cut journey times from months to days. The telephone turned the world into a cozier, nearer place. Each technological advance compressed certain distances, making some futures more reachable. But the underlying thermodynamic stream never reversed. Energies were consumed, heat was produced, and disorder still gently increased. In the slow calm of evolution and geology, time is written in layers. Trees keep silent rings for each season. Sediment lays down bands that become the pages of Earth's long, patient diary. Radioactive elements decay at predictable rates, and scientists read the ratios like a clock. These processes are statistical, steady, and irreversible. A fossil's age is a quiet testament to many tiny, one-way decays that marched ceaselessly toward stability. There are also moments where the universe surprises us with structures that appear to defy the ordinary drift toward disorder. Time crystals, for instance, are an exotic phase of matter that repeat in time rather than space. They cycle without losing energy in certain isolated contexts, but their perfection is constrained. They cannot power perpetual motion or rewrite the thermodynamic ledger. They exist in carefully controlled conditions, and even they bow to the general rule that the universe as a whole grows more disordered. Return now to the idea of perception. Our subjective sense of time can stretch and shrink like a soft accordion. When you are absorbed and joyful, hours feel like minutes. When you wait and worry, minutes can feel like an eternity. This is the dopamine effect at work. Our minds count more events when novelty is present and fewer when things repeat. The inner clock is not an exact metronome but a painting, an impression that changes with the colors of experience. That variability is gentle and kind. It reminds us that time's passage is not only physical but psychological, intimately tied to what we notice and what we allow to pass unnoticed. On the cosmic canvas, time has shape and destiny. Our universe began hot, dense, and astonishingly ordered in its way. Then came an incredible brief era of rapid expansion that smoothed and stretched space, leaving a low-entropy backdrop from which complexity would later arise. That early burst is part of the story that allowed stars to form and galaxies to bloom. The long trajectory that follows star formation, planetary systems, life, is a patient, never-rushed expression of the same slow thermodynamic flow. Think about stars for a moment. A star, like our sun, burns by turning light hydrogen into heavier elements. This act converts a simpler fuel into complex products while releasing enormous energy. The light leaves the star, bathing planets in warmth. Local order planets, life, the structure we cherish, arises from these processes, but always paid for by the heat and radiation thrown off into space. The star's life is an eloquent, slow enterprise, creation of structure in one place through the scattering of energy in another. Gently allow your mind to imagine the sound of a bell struck once in a vast cathedral. The bell rings, a loud, ordered wave of motion moving outward. Over time, the tone fades into air, the energy dispersing and the sound softening to nothing. No unseen hand gathers the sound back. The fade is irreversible, a simple sonic echo of entropy, ordered motion dissolving into random molecular jostle. The bell's lonely ring is a poetic snapshot of the same physical reality behind every ticking clock. In the human story, aging is a patient arrow. Cells divide, telomeres shorten, and the molecular machinery inexorably changes. Life cycles are sustained by countless chemical reactions, each consuming energy and increasing local entropy. The processes that sustain you are the same processes that slowly alter the tissues of your body. There is a certain soft beauty in this. Life blooms, persists, and returns, all part of the universe's patient accounting. We can also find comfort in the idea that the universe provides multiple clocks. There are atomic clocks, so precise they lose a second in millions of years. There are biological clocks, so intimate they keep your sleep and wake cycles in tune with the light. And there are cosmological clocks, so vast they measure the age of galaxies. Each clock has its domain and its cadence, and together they weave a quiet chorus that sings the same direction. At times, physics teases us with the idea that information might be lost forever. A black hole, as it swallows matter, hides the details of what fell in, at least from the outside perspective. This raises deep questions about whether the universe keeps a perfect ledger or if, at cosmic scales, some pages are sealed forever. The idea is unsettling and intriguing, but current theories suggest that information may not be truly destroyed. Rather, it is scrambled and redistributed in complex ways we are only beginning to understand. Regardless of the final word, the practical effect is the same. Once information is blurred into heat and randomness, recovering it is not something the universe tends to do. Now think of the light streaming from distant stars. Each photon has traveled for years, even millions or billions of years, to reach your eye. The light you see tonight left its source long ago. It carries with it a story of the past, the colors and intensities shaped by ancient events. Looking at starlight is like reading a letter from the deep past. The farther the light, the older the letter. The universe is full of such messages, and we receive them always in one temporal direction. There is also the idea of causal structure. Cause precedes effect, and this ordering is built into the fabric of spacetime. If information could travel faster than light, cause and effect would become muddled, and the neat tapestry of events we rely upon would fray. The constancy of light's speed is a silent guardian of causality, and it helps preserve a coherent arrow. Actions lead to outcomes, and the outcomes do not retroactively reshape their causes. Take a deep, slow breath. Imagine that you are a tiny particle drifting in a vast ocean of time. Sometimes the current speeds you along, sometimes eddies swirl you in calm circles. Yet the water's general flow is onward. You are part of a grand, patient river, and that river is full of beauty, complexity, and gentle surprises. The study of chaos shows us another subject of gentle wonder. In chaotic systems, tiny differences at the start amplify into large differences later. The weather, for instance, depends sensitively on initial conditions. The butterfly effect is not a magical prophecy, but a mathematical observation. Precise reversibility is impossible when you cannot know every tiny detail. This fundamental unpredictability gives the arrow of time a human-friendly feature. Even if the underlying micro-laws were reversible, our ignorance and the practical impossibility of perfect control mean we perceive processes as moving forward, never back. Let your mind slow further. Consider that the universe's long-term destiny may be a quiet, expanding emptiness in which stars burn out and temperatures cool. Scientists sometimes call this the slow heat death, a vast future of nearly uniform low-energy radiation. It is a landscape of gentle endings, not dramatic finales. The thought can feel melancholy, or it can be strangely comforting, a vast, tranquil close to a long, creative experiment. One of the most calming scientific facts is that much of what matters to us is local and beautifully immediate. The sun's warmth, a child's laughter, the rustle of leaves, these are the phenomena that contain most of our direct concerns and pleasures. The deep cosmological tides run slowly beside our lives, and yet they give our short human days context and depth. Knowing that we are part of a long, patient story can soften the sharpness of daily anxieties. It situates us within a grand narrative that values gradual processes and enduring connections. As we near the end of this gentle walk, allow yourself a final quiet reflection on the block universe idea. Some scientists suggest that every moment, past, present, and future, exists together in a four-dimensional structure, like a landscape. We traverse that landscape in a particular direction. Our experience of now is our personal path through the terrain. Whether one prefers to think of time as flowing or as a vast block of moments, both images remind us that time's passage is deeply tied to perspective. The feeling of moving forward is real, and our memories and anticipations weave together to create meaning. Slowly bring your attention back to your breath. Inhale calmly, exhale with a soft sigh. Notice your body accepting the present moment. Notice how your thoughts have become a little more spacious, like the sky after a storm. As you drift towards sleep, remember the many gentle faces of time we explored. The microscopic symmetries and the macroscopic drift, the star-forged orders balanced by dispersed heat, the clocks that tick by burning tiny bits of order, and the human mind that stretches experience like elastic. Time is not a harsh master. It is a subtle, patient companion, shaping and cradling change in a way that makes life possible. Time is not a harsh master. It is a subtle, patient companion, shaping and cradling change in a way that makes life possible. And as you lie here, listening softly, you may notice how time touches everything around you in gentle, almost invisible ways. Even the air in your room is slowly mixing, equalizing, drifting toward the same temperature everywhere. Warm pockets dissolve into cooler ones. Stillness spreads. This quiet, natural balancing act is another expression of time's steady direction, always smoothing, always settling, always guiding the world toward equilibrium. Consider the gentle ticking of your own heartbeat. Every beat is a tiny release of energy, a subtle confirmation that time is moving. Your heart cannot beat backward. It can only flow forward, carrying nutrients, carrying warmth, carrying life. Each pulse is both a reminder and a reassurance that you are here, that you are present, drifting along with the universe rather than against it. Your breath, too, has its own arrow. The inhale gathers, organizes, and draws in the air. The exhale releases, softens, and lets go. Breathing is a microcosm of time's nature. Effort followed by release, order followed by dispersal, tension followed by rest. Even in your own lungs, entropy gently guides the exchange of gases, and every breath is a quiet affirmation of the same universal rhythm playing out among galaxies. Now imagine Earth's oceans, slowly shifting with the tides. The moon's gravitational tug pulls the water in long, graceful sweeps. Every tide is a slow transfer of energy, friction between Earth and the moon's pull. With each cycle, Earth rotates just a little more slowly. Over billions of years, these tiny losses add up, lengthening the day by fractions of a second. The tides themselves are like the planet's breathing, an ancient, patient reminder that time acts even on worlds. Even mountains, which appear unchanging and eternal, are slowly wearing away. Wind lifts grains of dust. Water slips into cracks and expands when it freezes. Sunlight warms the rock by day and cools it by night, making it swell and contract in endless, gentle cycles. Over vast stretches of time, entire ranges rise and fall, sculpted by a million small processes that move in one unbroken direction. Even the oldest stones carry the fingerprint of time in their textures and layers. Shift your attention now to the night sky, the stars, the planets, the faint glow of distant galaxies. Every star you see is moving. Every galaxy is drifting outward as the universe expands. Light itself stretches as it travels, its wavelengths pulled longer and redder by the expansion of space. This cosmic redshift is time's signature written across the sky, a soft, universal whisper reminding us that everything is, slowly, gently, drifting outward. You are part of that drift. Every cell in your body contains atoms forged in ancient stars, atoms that have traveled for billions of years, changing, reacting, bonding, releasing energy, and moving forward through time long before you were born. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it is ancient matter shaped by the same unfolding arrow. Let this thought bring you comfort. Time is not something external pressing against you. You are made of it. You are built from its long flow. Your story is woven from countless irreversible steps the universe took long before you opened your eyes. You are the continuation of a cosmic journey that began with the first sparks of creation. And just like the universe, your mind also shifts and softens over time. New ideas settle where old ones once lived. Memories gently blur at the edges, not because they are lost, but because the brain reshapes itself to make room for the experiences that matter most. Forgetting is not a failure. It is a quiet biological process, a letting go that mirrors the way the world naturally relaxes into simpler, more peaceful states. Consider also the subtle way light fades at sunset. The sky transitions through warm golds, quiet pinks, and deep blues, each color a result of particles scattering sunlight into gentler forms. The day does not snap into night. Instead, it glides, letting go little by little, allowing your senses to adjust in a fluid, calm descent. This slow dimming is another reflection of time's character, never abrupt, never harsh, always smoothing edges and softening transitions. Now picture a quiet snowfall. Each snowflake falls with its own delicate pattern, its own tiny crystalline order. As they land, they form drifts of intricate chaos, a blanket that is both structured and random. Over time, sunlight melts the snow, turning it back into water that sinks into the earth. The snow does not reassemble into the flakes it once was. Instead, it continues its natural cycle, gently changing forms. In this way, winter teaches us about the impermanence of all arrangements and the peaceful surrender that drives time's gentle steps. Let yourself sink deeper into the present moment. The muscles in your face loosen. Your jaw relaxes. Your shoulders soften. You are not separate from time's flow, you are floating in it. There is nothing you must hold on to and nowhere you must go. The river carries you. It's comforting to realize that the universe doesn't hurry. Stars take millions of years to form. Planets cool over eons. Even light, the fastest thing in existence, takes time to cross the vastness of space. Nothing in nature is rushed. Everything unfolds at the pace it needs. And here, in your quiet place, you are allowed to unfold slowly too. Think of your own lifetime, not as a deadline, but as a long, warm thread stretched across moments you will cherish. Each memory you create is stored by a process that leaves a slight physical imprint, and every imprint is a testament to your experiences, your growth, your presence in this world. Time gives these moments context, giving weight to joy, meaning to challenge, and softness to the moments you choose to let go. As you rest, the world continues its patient unfolding. Trees grow rings, rivers carve valleys, winds shape dunes, clouds drift and disappear. Every part of nature follows the gentle pull toward balance, the same pull that guides your body, your breath, your thoughts into deeper stillness. And as you drift into this gentle flow, let your awareness stretch just a little wider, like a soft blanket unfolding across a quiet room. Time, for all its vastness, is also intimate. It is present in the tiniest vibrations, in the smallest flickers of energy, in the faint whisper of atoms rearranging themselves within every cell of your body. Consider the rhythm of your thoughts. Neural signals travel through your brain in waves, electrical pulses guided by ions moving through delicate channels. Each pulse is a cascade of microscopic changes, ordered states turning into slightly more disordered states, releasing just a tiny bit of heat. These signals are not reversible. They always travel forward, building the narrative of your mind step by gentle step. Your very ability to think is rooted in a process that carries time's arrow. This means something deeply comforting. Your consciousness unfolds naturally in harmony with the universe. You do not have to force it. You do not have to control it. You can simply let yourself be carried. Now, imagine the soft drift of clouds across the sky. They move with no urgency, shaped only by the wind and the warmth of the sun. Their forms shift slowly, dissolving, reforming, each change an expression of the same quiet principle guiding everything else. Clouds never reassemble into their exact former shapes. They evolve gently, like your thoughts as you fall asleep. As you picture this sky, Notice how your breath has begun to mimic that same slow drift. Rising, falling, rising, falling. Just like the clouds, your body moves in smooth transitions, carried by time at a pace that requires no effort. Drift now to a more ancient rhythm, the shifting of seasons. Spring warms into summer, summer cools into autumn, autumn folds gently into winter. No season reverses itself. No winter snaps back into the exact autumn that came before. Instead, the cycle moves forward in long, graceful loops, each year leaving soft imprints on the world. New growth, fallen leaves, melted snow, quiet seeds waiting for light. You too carry these seasonal imprints, moments of warmth, moments of change, moments of stillness, all guided by the same patient flow. Even the quiet flow of rivers mirrors this. Water starts as droplets in clouds, falls to earth, gathers into streams, and eventually journeys into the sea. It may evaporate and rise again, but never along the same exact path. Each journey is unique, familiar, but new. The river's motion is irreversible but comforting, a reminder that change can be soft, gentle, and endlessly renewed. Let this truth settle into you. Time does not erase, it transforms. It rearranges, it shifts, it softens the hard edges of memory. It carries you to new places, even while allowing you to rest in the peace of the present. Now imagine yourself standing at the edge of a vast desert at dusk. The sun is lowering, casting long golden shadows across the dunes. The sand shifts subtly with the breeze. Each grain is following its own small, irreversible path, carried by wind, by weight, by gravity. Over centuries, entire dunes migrate slowly across the land, not rushed, not abrupt, but with the patience of deep time. This desert, quiet and untouched, represents a truth about time. Great changes happen gently. You do not notice their motion moment to moment, but when you look back, you see how far they have traveled. In your own life, this is true as well. You grow quietly. You heal quietly. You learn quietly. You become who you are through countless small, irreversible steps, each one shaping you with care. Now let your mind float to a forest, deep and green, where time expresses itself through growth rather than motion. Trees add rings so thin you could barely see them, yet over decades these rings reveal the full story of their lives. Years of drought, years of abundance, years of storms, years of calm. A tree grows so slowly you never witness the change directly, but you know it is happening. You trust it. And just like the tree, you are changing in ways that are gentle, gradual, and steady, even now as you rest. Growth does not require effort. It happens simply because you exist. Now imagine a distant lighthouse on a quiet shoreline, its beams sweeping across dark waves in slow, rhythmic arcs. The light circles again and again, not hurried, not urgent. Each rotation marks time's passage but also provides guidance, comfort, and continuity. It reminds ships that they are not alone in the vastness. Time, too, is a lighthouse. It keeps watch. It guides you steadily forward, even when the waters of life feel open and endless. Let your breath follow that gentle rhythm, a soft sweep, and another, the deeper mysteries of time, even the ones scientists debate, all circle back to the same soothing truth. The universe moves forward in the direction of greater relaxation. Heat spreads out. Energy settles. Structures soften. Everything drifts toward a state of ease. And tonight, you are drifting with it. As you continue to relax, imagine the universe not as a place of ticking seconds, but as a wide, warm field of moments. You walk across this field slowly, barefoot, feeling the grass sway around you. Every step presses gently into the earth, and the impression fades naturally as the blades rise back up. No footprint returns precisely the same. Each moment passes gracefully into the next. You are safe in this field. You are held. You are unhurried. Even your dreams are shaped by time's soft hand. Memories mix, imagery bends, moments unfold without structure or pressure. Dreams are the mind's way of participating in the universe's long tradition of rearranging, redistributing, and softening. Dreams, too, drift forward. Dreams, too, dissolve gently into morning light. Now notice how your body feels, heavier, softer, warmer, wrapped in the quiet understanding that nothing is required of you right now. No tasks, no decisions, no effort, nothing but rest. Time continues its gentle flow whether you are awake or asleep. You do not have to steer it. You do not have to think about it. You can simply let go and allow yourself to be carried the way a leaf floats on a calm stream. Each moment brings you closer to deeper rest. Each breath leads you further into calm. Each heartbeat softens you into sleep. This disagreement isn't confusion, it's physics. Different observers genuinely experience different present moments. This means the flow of time is deeply tied to motion, and no single definition of now exists for the entire universe. Another striking fact comes from muons, tiny particles created when cosmic rays collide with Earth's atmosphere. Muons live extremely short lives, about 2/millionths of a second. At rest, they should decay long before reaching Earth's surface. Yet millions of them do reach the surface. Why? Because their high-speed motion slows their internal clocks. They live longer from our perspective, providing direct, measurable proof of time dilation happening above your head every second of every day. Now let's move to gravitational lensing, the bending of light around massive objects like galaxies or black holes. Here's the time-related part. When light bends around a massive object, it doesn't just curve, it also experiences a delay. This Shapiro delay means that gravity literally slows the passage of time along light's path. Some distant galaxies appear duplicated in the sky because their light takes multiple different paths around a massive object, each path taking a different amount of time. The night sky is full of echoes, some arriving thousands of years apart. Another fascinating time-related phenomenon involves synchronizing clocks. It might sound simple, but the deeper you go, the stranger it becomes. Two identical clocks, synchronized perfectly, will fall out of sync if one is closer to a massive object, one travels faster, one accelerates, one experiences slightly different gravity. This means that the idea of a universal clock, a single cosmic timekeeper, is impossible. Each clock in the universe experiences its own private passage of time. Let's turn now to antimatter. Some interpretations of quantum field theory view antimatter as ordinary matter moving backward in time mathematically. This doesn't mean antimatter literally travels backward in our everyday world, but in certain diagrams, reversing time and swapping particles with antiparticles gives identical results. This symmetry is elegant but fragile. Tiny observed violations are among the few clues we have that real physical time prefers one direction. Now, imagine the early universe, when temperatures were unimaginably high. Back then, particles and antiparticles were produced in equal amounts, perfect symmetry. Yet something tipped the balance so that matter slightly outnumbered antimatter. This tiny bias, roughly one extra matter particle per billion, is the reason anything exists at all. Had the universe been perfectly symmetric in time and matter flow, everything would have annihilated into light, leaving no stars, no planets, no life. The existence of matter itself is evidence that time had a preferred direction built in from the beginning. Let's step into a different domain, time in biology. Every living organism depends on biochemical reactions that operate in one direction. Cells break down molecules, release energy as heat, and use that energy to build more complex structures. None of these reactions are reversible in real life, even if they are theoretically reversible in equations. Once energy disperses as heat in a cell, it cannot be recollected into the exact state it came from. This irreversible chemistry forms the backbone of biological time, growth, aging, memory, and metabolism. Next, consider sands in an hourglass. Though incredibly simple, an hourglass is governed by complex granular physics. The flow of sand is irreversible. Once grains fall and settle, they will not spontaneously return to the top chamber. If you film an hourglass upside down, sand flying upward, the video looks obviously wrong. Your brain's instinctive detection of wrongness is based on a lifetime of observing entropy at work. Even your intuition is partially trained by thermodynamic time. Now let's move to crystal growth. When certain crystals form, they grow outward in beautiful, intricate shapes. But the process requires the release of energy into the surroundings. Local order increases, but the environment becomes more disordered. This is why crystals can grow spontaneously, but they never spontaneously shrink into solution and reassemble into their original molecular configuration. Time, again, enforces direction through energetics. Another concept worth exploring is cosmic redshift. Light from distant galaxies is stretched into longer wavelengths as the universe expands. The more distant the galaxy, the greater the redshift, meaning the light is older, and the universe was younger when it began its journey. Every photon is a time capsule, carrying with it a timestamp encoded in its wavelength. The redder the light, the deeper into the past we are looking. Now consider the cosmological horizon, the boundary beyond which light has not had enough time to reach us since the Big Bang. This horizon is constantly expanding, revealing more of the universe as time passes. The simple fact that this horizon grows, never shrinks, is another irreversible phenomenon tied directly to cosmic time. Let's turn to something more grounded: friction. Friction is one of the most familiar irreversible forces. Whenever two surfaces rub together, microscopic bumps collide and deform, producing heat. That heat dissipates into the environment and is effectively lost. Friction is why machines wear down, why engines need oil, why moving parts stop. It is entropy in motion, and it ensures objects do not spontaneously regain their original energy and motion. Now let's explore the origin of the second. Modern timekeeping defines 1 second as the duration of exactly 9,192,631,770 vibrations of a cesium-133 atom. This definition is astonishingly precise. Atomic clocks are so accurate that over the age of the Earth, 4.5 billion years, they would be off by less than a minute. This precision is necessary for GPS, telecommunications, satellites, and scientific measurement. Yet even these perfect clocks require corrections for relativity. Even our best tools for measuring time cannot escape the rules of time itself. Another subtle time phenomenon is phase transitions. When water freezes or boils, it undergoes an irreversible transformation. The molecules lose or gain energy, and the system moves toward a more probable state under changing conditions. You never see steam spontaneously condense into liquid water that reheats and boils itself back into vapor without external energy. Everyday phase changes are simple examples of microscopic irreversibility playing out at human scales. Let's wander back to the cosmic scale for a moment. The cosmic microwave background, CMB, slowly cools over time as the universe expands. Right now, it is about 2.7 Kelvin. Trillions of years from now, it will be colder, stretched into lower energy wavelengths. This gradual cooling is one of the clearest indicators that the universe is aging, a cooling clock ticking in the background of all existence. Another remarkable fact: quantum tunneling can allow particles to skip forward in space, but not backward in time. A particle can appear on the other side of an energy barrier without traveling through it, a bizarre quantum trick. But tunneling does not reverse entropy. It does not restore past states. Even the strangest quantum shortcuts respect the one-way flow. Let's touch on LIGO gravitational wave detections again. When two black holes merge, they release more energy in a fraction of a second than all the stars in the observable universe combined, but in gravitational waves, not light. That energy radiates outward forever. Nothing can bring it back. It is pure irreversible loss, the loudest possible confirmation of time's direction. Now consider thermal equilibrium. Left alone, any system tends toward uniform temperature. Hot regions cool, cold regions warm, until everything matches. This final state contains maximum disorder and no gradients to drive change. Once equilibrium is reached, no spontaneous reversal occurs. This tendency toward uniformity is one of the deepest hallmarks of entropy. Another intriguing fact: matter itself slowly decays. Protons, once thought to be eternal, may have a half-life of around 1033 years or more. If proton decay is real, then all matter will eventually dissolve into simpler particles. Even the atoms in your body, your room, and the Earth may eventually decay in deep future eras. That decay is irreversible, yet another long-term clock ticking quietly across the cosmos. One of the most remarkable demonstrations of time's slow influence is found in glacial ice. Deep within Antarctica and Greenland are layers of ice stretching hundreds of thousands of years downward. Each winter snowfall compresses the layers beneath it, trapping tiny bubbles of ancient air. By drilling ice cores, scientists have reconstructed a chronological record of Earth's atmosphere, concentration of carbon dioxide, traces of volcanic eruptions, patterns of climate change, all preserved in chronological layers like pages in a frozen diary. The deeper the ice, the older the air. The oldest ice core samples contain air from more than 800,000 years ago, a direct inhale from a world long gone. If you were to melt a sample, you would release molecules that last floated freely in the ancient sky above long-vanished landscapes. This is time made physical, a frozen archive recording Earth's breath across millennia. Another natural archive resides in tree rings. Each ring marks a year of growth, with thick rings representing wet, warm years and thin rings reflecting drought or stress. Dendrochronology, the study of tree rings, allows scientists to date wooden artifacts, reconstruct climate history, and even pinpoint the exact year of ancient volcanic eruptions. Trees, without ever intending to, create calendars of their own lives, ring by ring. Even more astonishing is that each ring contains isotopic signatures, revealing solar activity and atmospheric composition at the time it formed. A tree growing quietly in a forest is unconsciously storing information about time encoded in the chemistry of its wood. Let's step to a far larger scale now: galactic rotation curves. Spiral galaxies, including our Milky Way, rotate like giant cosmic pinwheels, but they don't rotate the way you might expect. Stars near the edges of galaxies orbit at nearly the same speed as stars near the center. According to classical physics, this should be impossible unless something unseen is providing extra gravitational pull. That something is dark matter. The existence of dark matter is inferred by watching how galaxies evolve over billions of years. Without dark matter, galaxies would come apart as they spin. The way galactic structure survives across cosmic time is one of the clearest clues that a massive, invisible substance is shaping the universe. Time, again, is revealed through endurance. The longevity of galaxies proves the presence of something we cannot see, but which has shaped cosmic history from the beginning. Now turn your attention to tidal forces, the gravitational interactions between Earth, the Moon, and the Sun. Every tide is a slow exchange of angular momentum. Earth's rotation gradually slows because the Moon's gravity tugs on the oceans. Meanwhile, the moon slowly drifts farther away, about 3.8 centimeters per year. This means the moon used to appear larger in the sky, and Earth's days were shorter. Hundreds of millions of years ago, a day lasted roughly 22 hours, and the moon was noticeably closer. In fossil corals, scientists find growth rings that record daily and yearly cycles. Those rings show that ancient Earth experienced more days per year, confirming that Earth's rotation has indeed been slowing over time. This connection between fossils and celestial mechanics is one of the most beautiful in science, living creatures storing evidence of astronomical change in their bodies. Consider now the quiet drift of continental plates. Continents move a few centimeters per year, about as fast as your fingernails grow. Over millions of years, this slow motion rearranges entire worlds. Mountains rise, oceans split, deserts migrate, and new climates emerge. The Himalayas, for example, formed when India drifted northward and collided with Asia roughly 50 million years ago. This gentle but persistent movement is driven by heat escaping from Earth's interior, a process governed by radioactive decay, one of nature's most reliable timekeepers. Each shift in the Earth's crust is another stroke in the planet's grand clock, marking ages that last far beyond human history. Another fascinating time phenomenon appears in supernova remnants. When a star explodes, it casts out expanding shells of gas and dust. Astronomers can observe these shells and watch how fast they spread to estimate the moment of the explosion. In some famous cases, such as the Crab Nebula, the expansion can be traced back to historical astronomical records. Chinese astronomers documented a bright guest star in 1054 AD. Today, we can study its lingering remains. The universe is full of fading signatures of ancient events, each expanding cloud a timestamp in the cosmic calendar. Let's move to radioactive clocks, which allow us to measure deep time in rocks, fossils, and meteorites. Different isotopes decay at different rates, known as half-lives. Uranium-238 has a half-life of 4.5 billion years, nearly the age of the Earth. Potassium-40 decays into argon at a steady, predictable rate, providing another geological clock. With these tools, scientists determined that Earth formed around 4.54 billion years ago, a number anchored entirely in the slow, irreversible decay of atomic nuclei. Every speck of dust, every stone, every mountain quietly contains atoms ticking down in perfect rhythm. Now, let's explore synchronicity in biological rhythms. Many organisms use environmental cues to regulate their internal clocks. A striking example is the 17-year periodic cicada. These insects spend most of their lives underground, emerging only after exactly 17 years to reproduce in enormous synchronized swarms. The precision of this timing reflects a deeply embedded evolutionary clock. Another example is the behavior of birds that use the Earth's magnetic field, which changes slowly over time, to navigate during migration. Even slight shifts in the magnetic poles alter migration routes. In this sense, Earth's magnetic field becomes another slow-moving clock, gently influencing life across millennia. Let's explore one of the universe's most elegant time-related illusions: look-back time. When you observe a star that is 1,000 light-years away, you are not seeing it as it is now. You are seeing it as it was 1,000 years ago, because that is how long its light took to reach you. Telescopes are therefore not tools for observing the present, they are tools for observing the past. The most distant galaxies visible today appear as they existed more than 13 billion years ago, shortly after the Big Bang. Every image we capture is a window into a different era. To look farther away is literally to look deeper into history. Next, consider cosmic expansion, discovered by Edwin Hubble in the 1920s. He found that galaxies move away from us at speeds proportional to their distance. The farther the galaxy, the faster it recedes. This expansion stretches space itself over time. Even if galaxies were frozen in place, the space between them would grow. This expansion has profound consequences. It sets a limit to how far we can see, and it ensures that some distant galaxies will eventually slip out of view forever as their light becomes too stretched to reach us. Time here becomes geography. The shape of the universe determines what eras we can access. Another important concept is the Planck time, the smallest meaningful unit of time in physics. If true, the apparent flow of time might be built from countless indivisible steps, like frames in a film. Now let's turn to the Anthropocene clock, the idea that human activity leaves measurable geological traces. Plastics in the sediment, radioactive fallout from nuclear tests, and industrial chemicals are all long-lasting markers that future scientists or alien archaeologists could use to date our era. We are, in a sense, engraving our presence into deep time. Another strange but powerful concept is cosmological time symmetry. Some theories suggest the universe might have a mirror counterpart running backward in time relative to ours. In this speculative model, the Big Bang produced two universes expanding in opposite temporal directions. In that mirror universe, we would appear to be the ones moving backward in time. Though still theoretical, this idea would elegantly restore symmetry to the laws of physics without changing our lived experience. Now consider the speed of time in a gravitational well. If you stand on a neutron star, a collapsed stellar core so dense that a teaspoon of its material weighs as much as Mount Everest, time would pass dramatically slower for you than for someone on Earth. A single second on a neutron star could correspond to hours or even days elsewhere. Gravity doesn't just bend space, it stretches time itself. Speaking of stars, their life cycles serve as cosmic clocks. Massive stars burn quickly and live short, brilliant lives, sometimes only a few million years. Smaller stars like our Sun burn more slowly, lasting billions of years. Red dwarf stars burn so efficiently that they can survive for trillions of years, far longer than the current age of the universe. If looking for life in the distant future, red dwarfs will likely be the final long-lived hosts of habitable planets. Let's explore chaos in planetary orbits. While the solar system appears stable, long-term simulations show that planetary orbits are chaotic over extremely long timescales. Tiny gravitational nudges accumulate, and after hundreds of millions or billions of years, orbits can shift significantly. This means that even celestial mechanics, which appear deterministic, are subject to the irreversible march of unpredictable change. Another fascinating time-related concept is the eternal inflation model, which suggests that new universes may constantly be forming in a vast multiverse. In this framework, time itself may branch endlessly as new regions of spacetime expand. Our universe might be just one bubble in an infinite foam, each with its own arrow of time and its own laws. Now let's consider thermal time, the idea that time may not be fundamental at all, but could emerge from the statistical behavior of systems in equilibrium. In this view, time is a side effect of temperature, entropy, and probability. Remove temperature differences, and time might vanish as a meaningful concept. This idea challenges our intuition, but fits surprisingly well with how the arrow of time aligns with entropy. Let's also explore the role of quasars, ancient cosmic engines powered by supermassive black holes. Quasars shine so brightly that they can be seen across billions of light years, but they existed primarily in the early universe. By studying their light, astronomers can date epochs of galaxy formation and cosmic evolution. Quasars serve as lighthouses marking the universe's adolescence, bright, distant timestamps carved into spacetime. Finally, consider the ultimate fate of time. Far in the future, the universe may reach a state where no usable energy remains. Stars will fade, black holes will evaporate, and matter will decay. When all gradients are gone, nothing more can happen, no reactions, no motion, no change. Without change, time loses meaning. It is not that time ends dramatically. It simply becomes irrelevant, like a clock in a featureless, unchanging desert. In this distant, silent era, time becomes a shadow of its former self, a relic of a universe that once pulsed with stars and life and motion. As we continue drifting through the landscape of time, let's move into some of the most intriguing and lesser-known mechanisms by which the universe measures, bends, archives, and sometimes disguises the passage of moments. One of the most elegant timekeepers in nature is the pulsar. A pulsar is the collapsed core of a massive star that once exploded in a supernova. After the explosion, the remaining neutron star rotates with astonishing speed while emitting beams of electromagnetic radiation from its magnetic poles. As those beams sweep across space, they pass Earth at perfectly timed intervals, much like the rotating beam of a lighthouse. Some pulsars rotate hundreds of times per second with such stability that they rival atomic clocks. Scientists use pulsars to measure cosmic distances, detect gravitational waves, and test the limits of general relativity. The universe builds clocks out of dead stars, and they keep time by spinning forever in the darkness. Another remarkable natural clock lies at the heart of every cell, the molecular circadian oscillator. Inside your body, proteins follow a cycle of production, accumulation, suppression, and decay that repeats roughly every 24 hours. These cellular rhythms continue even when isolated from light or temperature cues. Every cell in your body carries a microscopic clock whose gears are made of chemistry, and these clocks collectively synchronize through hormonal signals, light exposure, and temperature changes. Your feeling of morning alertness or evening drowsiness is not merely psychological. It is the result of billions of tiny chemical clocks ticking in unison. Let's step away from biology for a moment and consider something older and colder: the half-life of cosmic rays. High-energy particles constantly bombard Earth from distant supernova and black hole jets. When they strike atoms in the atmosphere, they produce carbon-14, the isotope used in radiocarbon dating. Living organisms absorb carbon-14 while alive, but once they die, the carbon decays at a predictable rate. By measuring the remaining carbon-14 in ancient wood, bones, or textiles, scientists can estimate ages up to around 50,000 years. This decay process has been used to date cave paintings, Ice Age fossils, ancient manuscripts, and even determine whether historical garments are genuine or counterfeit. Time quietly leaves fingerprints in carbon itself. Another deeply calming and fascinating process is stellar metallicity, the way stars change over time by synthesizing elements heavier than helium. Older stars contain almost no metals in astronomy. Metals mean anything heavier than helium. Younger stars contain more because previous generations of stars created and scattered those elements when they died. By studying a star's chemical composition, astronomers can estimate when it formed in the timeline of the galaxy. The universe marks its ages not with calendars, but with the slow enrichment of elements forged in starlight. Think now of the tidal evolution of planetary systems. When a planet orbits very close to its star, tidal forces can gradually change the orbit. Some planets spiral inward and eventually burn up or disintegrate. Others spiral outward and drift into safer, more distant paths. This slow dance unfolds over millions or billions of years, yet the outcome leaves detectable signatures: unusually long days, strange orbital resonances, or planets locked with one side permanently facing the star. Even exoplanets we will never visit carry the imprint of time in their tilts, rotations, and orbital shapes. The Earth itself carries ancient scars that reveal its long history. Consider craton formation, the ancient, stable cores of continents. These pieces of the lithosphere have survived relatively unchanged for billions of years. Found beneath regions like Australia, Canada, and parts of Africa, cratons form the oldest surfaces on Earth. They are geological time capsules, storing chemical and mineral evidence of the early planet, from the first oceans to the first atmosphere and the earliest continental crust. Standing on a craton is standing on a fragment of Earth's most ancient time. Let's travel deeper still into the mechanics of time by exploring quantum decoherence, a phenomenon that prevents quantum systems from staying in superposition at macroscopic scales. Quantum behavior thrives only when systems remain isolated from the environment. But in the real world, particles constantly collide, interact, and exchange energy. This interaction forces quantum states to collapse into definite outcomes. It is a subtle, irreversible process, and one of the foundations of the arrow of time at the quantum scale. Decoherence ensures that macroscopic objects, chairs, planets, people, behave classically, not quantum mechanically. In essence, the universe's inexhaustible interactions create the flow of time by erasing quantum ambiguity. Now consider cosmic background neutrinos, remnants of the Big Bang. Just as the cosmic microwave background is a snapshot of the early universe's radiation, the cosmic neutrino background is a relic of the first second after the Big Bang. These neutrinos have been traveling freely through the universe for nearly 14 billion years. They carry information from an era long before atoms existed. Detecting them is exceedingly difficult, but their theoretical properties serve as one more silent clock measuring the universe's age and evolution. Let's shift our focus to something far more tangible: mountain erosion. Mountains rise when tectonic plates collide, but they do not remain tall forever. Rain, ice, glaciers, and wind wear them down. The Appalachian Mountains in eastern North America were once as tall as the Himalayas, but have eroded over hundreds of millions of years into the softer, rounder shapes we see today. Every rounded peak, every smooth ridge, is a monument not only to geology but to time itself, the slow, ceaseless sculpting of an entire continent. Another process shaped by time is planetary differentiation. When planets formed, they heated through repeated collisions and radioactive decay. This allowed molten materials to separate according to density. Heavy metals sank into cores, while lighter materials rose to form mantles and crusts. This sorting process created magnetic fields, volcanic activity, and the internal heat that still drives plate tectonics. Earth's iron core is more than 4 billion years old. Its magnetic field is a long-term consequence of ancient differentiation. Our compasses work today because molten iron continues to flow deep beneath our feet, following a rhythm that began in Earth's earliest youth. Now consider supermassive black hole mergers, immense cosmic collisions that occur when two galaxies merge. As the central black holes spiral into one another, they emit gravitational waves that ripple across spacetime. These waves stretch and compress space itself. By detecting them, scientists can determine the masses, spins, and distances of the merging black holes. Each detected gravitational wave carries with it the timestamp of an event that happened billions of years ago, long before the Earth formed. The universe broadcasts its history in vibrations that we can now capture. One of the most subtle time-related phenomena is proton decay, which, if it exists, would be an unimaginably slow process. Some theories predict that protons, the stable particles that make up atoms, may eventually decay over time spans longer than 1034 years. No such decay has been observed, but if it occurs, it would mean that even matter itself is not eternal. In a far, far future, the universe's last atoms might slowly disintegrate, leaving only radiation. Whether or not proton decay exists, the idea illustrates humanity's attempt to understand time not just across billions of years, but across Google years, time scales almost beyond imagination. Another fascinating concept is the cosmic event horizon. Because the universe is expanding, there are regions of space whose light will never reach us, no matter how long we wait. These galaxies are receding faster than light due to the expansion of space itself. We cannot observe them; they are permanently beyond our horizon. This horizon grows and changes with cosmic expansion, shaping the part of the universe we can ever know. Time and distance blend into one. Every moment that passes pushes more galaxies out of our view forever. Closer to home, consider magnetic field reversals on Earth. Every few 100,000 years, Earth's magnetic field flips, with the north and south magnetic poles switching places. These reversals leave imprints in volcanic rock, as the iron-rich minerals align with the current magnetic field at the time of their cooling. By studying these rocks, scientists have reconstructed a timeline of magnetic flips stretching back hundreds of millions of years. The ocean floor contains these magnetic stripes, chronological layers on either side of mid-ocean ridges that record the steady creation of new crust. Earth's geology is full of magnetic timestamps. Let's move now to the concept of entropy in information systems, a digital signature of time. Whenever data is erased from a computer drive, heat is produced. This is Landauer's principle. Erasing one bit of information generates a minimum amount of entropy. This means that simply deleting a file is a thermodynamic event. Information storage and destruction are physically tied to the arrow of time, reminding us that even our most modern technologies obey the ancient rule of irreversible increase in entropy. Another subtle time marker lies in the decay of planetary orbits due to gravitational radiation. The Hull-Staler binary pulsar is a pair of neutron stars orbiting each other. They lose energy over time by emitting gravitational waves, causing the orbit to shrink. We can predict exactly when the two stars will collide, in roughly 300 million years. This slow decay is a natural clock, ticking through gravitational loss. Let's consider something far more familiar: the speed of thought. Neural impulses in the brain travel at up to 120 meters per second, and complex thoughts involve cascades of chemical reactions and electrical patterns. Your perception of time's flow is influenced by how quickly your brain processes sensory input. Time appears slower when you take in more information per second, such as during danger, because the brain is operating at a heightened processing rate. This has been observed in athletes, pilots, and people experiencing adrenaline surges. Your mind's internal clock is elastic because its machinery is biological. Finally, let's return to the cosmic scale and consider the sun's future. In about 5 billion years, the sun will expand into a red giant, engulfing Mercury and Venus, and possibly Earth. During this phase, the sun's outer layers will cool and redden, even as its radius swells to hundreds of times its current size. Eventually, it will shed its outer layers to form a planetary nebula, leaving behind a white dwarf, a stellar ember that will cool for trillions of years. This slow fade from bright star to dim ember is the final, graceful arc of stellar time.